Welcome to all of you. Now we discuss MCQ 2023 Linear Programming Problem, Semester 5 CBCS Mathematics Honors, University of Calcutta. Question paper B.Sc B 1.2 Linear Programming and Game Theory 2023. Question 1a. Which of the following option determines the extreme points of the set S equal to the set of all those order pair points x, y such that x square by a square plus y square by b square less than equal to 1, x greater than equal to 0, y greater than equal to 0. First option is this 0, 0, a 0, 0, b. Second option, all points on the elliptical boundary. Third option, 0, 0, a 0, 0, b and all points on the elliptical boundary in the first quadrant. Option 4, none of the above. Now, x square by a square plus y square by b square equal to 1 represents an ellipse with semi-major axis this a and semi-minor axis b. We are interested only for the first quadrant because x greater than equal to 0, y greater than equal to 0. So we draw here the portion of the ellipse in the first quadrant only. Now this is the x square by a square plus y square by b square less than equal to 1 with this first quadrant. So this set, convex set, is the interior point and the boundary points this in the first quadrant S. Now extreme point or vertex point of this convex set S, a point X of a convex set C, a subset of n Euclidean space, n-dimensional Euclidean space, is said to be an extreme point of the set C if the point X does not lie on any line segment joining two other points of C. That is, for distinct points x1 and x2 belongs to C, X cannot be expressed as a linear combination of this, that is x equal to lambda x1 plus 1 minus lambda x2, 0 less than lambda less than 1. And this is the definition of convex point. So if this point is a convex point, so we cannot draw any line segment with the other 2 points on this set. Now a point x1 y1 which satisfy x1 square by a square plus y1 square by b square equal to 1 in the first quadrant is an extreme point. So obviously on the first quadrants on this boundary on this ellipse, that is this first, this is the thick boundary, this here, all points on this boundary line on the elliptical curve, this curve, all extreme points also. And hence 0, 0, this 0, 0 origin, and a 0, this point we say capital A, and this 0b, and all points on the elliptical boundary in the first quadrant. This is the all extreme points because say note this point, the extreme point, and we cannot draw any line segment other than 2 points of the convex set this on this. So this point does not lie any other lines, any line segment joining two other points on the convex set, this set. So correct option is 3. Next question 1b. The union of two convex sets, option 1 may or may not be a convex set, Option 2 must be a convex set. Option 3 must not be a convex set. Option 4 none of the above. The union of two convex sets may or may not be a convex set, but intersection always convex set. For example, consider x1 is the set of all those order pair points xy belongs to E2 such that x greater than equal to 10. So this x greater than equal to 10, so this is the this shaded region, this portion is the capital X1, this set, and x2 is this x less than equal to 5, so this portion this less than equal to 5. Obviously this capital X1 and this capital X2 are two convex sets, but x1 union x2 is not a convex set. Take any point a1 b1 on the set capital X1 and a2 b2 on the convex set capital X2, but the line segment joining these 2 points, this a1 b1 and a2 b2 does not lie on the union, because this portion does not lie any of these two sets. So the line segment joining these 2 points does not lie on x1 capital X1 union capital X2. So union may or may not be a convex set. Correct option is this. Next, question 1c, the solution first bracket 1 comma half comma 0 comma 0 comma 0 of the equation x1 plus 2x2 plus x3 plus x4 equal to 2, x1 plus 2x2 plus 1 by 2x3 plus x5 equal to 2 is option 1 a basic solution, option 2 not a basic solution, option 3 a basic feasible solution, option 4 a degenerate solution. Now the given system of linear equations can be written as in matrix form, this Ax equal to b. Obviously this A is the matrix 2 by 5 matrix, 2 rows and 5 columns, 2 by 5 matrix. Actually we multiply the second equation by 2 on both sides. So this 2x1 4x2 x3 plus 0x4 because x4 is absent here, and 2x5 this is equal to 2 into 2 4. So B column matrix 2 4 this. So A is the 2 by 5 matrix and corresponding x. Actually x, this capital X is the x1 x2 x3 x4 x5, actually the column matrix, that is, so with this 5 by 1, so this 2 by 1, so corresponding column matrix B is 2 by 1. Let this Ax equal to b equal to this can be represented as a1 x1 plus a2 x2 plus a3 x3 plus a4 x4 plus a5 x5 equal to b, where a1 is the column matrix this 1 2, a2 2 4 column matrix, a3 1 1, a4 1 0 and a5 0 2. Now the given solution is 0 half 0 0 0 0. So x1 is 1, x2 is half, and x3 x4 x5 are all zeros, as it satisfies the given equation. So if we put x1 equal to 1, x2 equal to half, x3 equal to 0, x4 equal to 0, x5 equal to 0, this solution satisfies this system. So this is a given solution. Now corresponding these associated column vectors of A corresponding to non-zero variables, this non-zero variables, this x1 and x2, so corresponding column vectors a1 and a2. Using a1 and a2 we get this determinant 1 2 2 4, and the value of the determinant is 0. So obviously these column vectors, this a1 and a2 are linearly dependent, hence the given solution is not a basic solution of the given system. Actually this is the non-basic feasible solution. This solution 1 half 0 0 0 non-basic feasible solution. because this determinant, corresponding determinant, non-zero variables, this 0. So this is not a basic solution of this. Hence the correct option is 2, is not a basic solution. Next question, 1D. Consider two sets capital X, the set of all those x1, x2 order pair, such that x1 plus x2 less than equal to 2, 2x1 plus 2x2 greater than equal to 8, x1 comma x2 greater than equal to 0, and y is the set of all those order pairs, this x1 comma x2, such that x1 square plus x2 square less than equal to 4. Then option 1, x is a convex set but y is not convex set. Option 2, x is not convex set but y is a convex set. Option 3, both x and y are convex sets. Option 4, none of x and y are convex sets. Now this x, capital X, this x1 plus x2 less than equal to 2, 2x1 plus 2x2 greater than equal to 8. First we draw the corresponding straight line, x1 plus x2 equal to 2. So x1 by 2 plus x2 by 2 equal to 1. So this 2 to this point, so this is the straight line, x1 plus x2 equal to 2. And 2x1 plus 2x2 equal to 8. So x1 by 4 plus x2 by 4, this is equal to 1. So this is the greater than equal to and this is the less than equal to. So corresponding shaded region, hence this capital X, this is a joining of these two portion. So obviously this capital X is not a convex set. And y, this is the circle with center at origin and radius 2, x1 square plus x2 square equal to 2 square and interior points. So obviously this is the convex set, y is a convex set. This hence this x is not convex set but y is a convex set. So by graphical diagram, so we can conclude that x is not a convex set and y is a convex set. Hence the correct option is 2. Question 1e. If any of the constraint in the primal problem be a perfect equality, then the corresponding dual variable is option 1 unrestricted in sign, option 2 positive, option 3 negative, option 4 0. We know the following theorem corresponding duality chapter. If the kth constraint of the primal problem is an equation, then the corresponding dual variable wk is unrestricted in sign. Hence correct option is 1, unrestricted in sign. Note that this primal and dual, corresponding primal say maximizing problem and this minimizing problem, then if ith constraint for primal is less than equal to type, then corresponding dual ith variable is greater than equal to 0. If for the primal ith constant is equal to type, then corresponding dual problem ith variable unrestricted in sign. And in the primal problem jth variable is greater than equal to 0, corresponding dual problem jth constant greater than equal to type. And in primal problem, if jth variable unrestricted in sign, and corresponding dual problem jth constant is equality type. So here correct option is 1. Question 1f. In a simplex method, if the optimality condition be satisfied at any iteration and if the basis containing one or more artificial vectors with corresponding artificial variable at 0 level, then the solution obtained is option 1 optimal, option 2 no feasible, Option 3 feasible but not optimal. Option 4 feasible but not basic. We know that in the optimal table, if one or more artificial vectors present in the basis and the corresponding artificial variables appears at zero level, then solution is optimal and hence the constraint equations are consistent, though one or more constraint may be redundant. So here correct option is 1, optimal. Question 1G. A degenerate basic feasible solution in a balanced transportation problem with m origins and n destinations will be consist of option 1 at least m plus n minus 1 positive variables, option 2 at most mn minus bracket m plus n minus 1 positive variables, option 3 at most m plus n minus 1 positive variables, option 4 at most m plus n minus 2 positive variables. Correct option is 4. We have theorem. In a balanced TP having m origins and n destinations where m and n greater than or equal to 2, the exact number of basic variables is m plus n minus 1. Now, when at least one basic variable of these m plus n minus 1 basic variables is 0, then solution is called a degenerate basic variable solution. So at least one is 0, so at most m plus n minus 2 positive variables corresponding basic variable solution, then this solution is degenerate. So for degenerate basic variable solution, we have at most m plus n minus 2 positive variables. Correct option is 4. Question 1H. If either of the primal or dual admits unbounded solution, then the other has option 1 one feasible solution, option 2 two feasible solutions, option 3 no feasible solution, option 4 infinite number of feasible solutions. Now we have unboundedness property. If the primal or dual problem has unbounded solution, then the corresponding dual, that is alternatively primal problem, has no feasible solutions. If we choose primal, then corresponding dual. If we choose here dual, then corresponding primal. So one has unbounded solution, then the corresponding dual or primal has no feasible solution. Actually, this is the proof for this theorem, that the primal problem has unbounded solution, then the objective function of that primal is unbounded. Now, the weak duality theorem states that any feasible solution to the dual would provide an upper bound of the primal objective function. Actually, theorem states that C transpose x bar less than equal to B transpose u bar. This u x transpose x bar transpose the feasible solution of the primal, this primal, and u bar transpose the feasible solution of the dual. Actually, you can omit this portion. Hence, the dual problem has no feasible solution. Since the dual of the dual is primal itself, so when dual admits unbounded solution, then the corresponding primal has no feasible solution. So correct option is 3, no feasible solution. Question 1I. In an assignment problem with m jobs and m machines, the number of basic variables at 0 level in a basic feasible solution is option 1 m, option 2 m minus 1, option 3 m plus 1, option 4 m minus 2. Now we know that for a non-degenerate basic feasible solution in a transportation problem, there are m plus n minus 1 basic variables at most. For this non-degenerate, so we have positive values m plus n minus 1. Since an assignment problem is a special case of the transportation problem, so for an assignment problem there are m plus m minus 1, that is twice m minus 1, because assignment problem is always square type. Here square type, so here m jobs m machines, so m plus m minus 1 is twice m minus 1 basic variables in a basic feasible solution of the corresponding assignment problem. But as is seen from the constraint that every basic feasible solution consists of m basic variables, each being equal to 1. So from this twice m minus 1 basic variables, we have m basic variable equal to 1. So remaining m minus 1 basic variables is equal to 0. So here the basic variables at 0 level, obviously m minus 1 number of basic variables at 0 level. So correct option is 2. Next question, last MCQ, J. 1J. In a game with 2 by 2 pair of matrix A, B, C, D, where A less than D less than B less than C, option 1, A is the saddle point, option 2, B is the saddle point, option 3, D is the saddle point, option 4, there is no saddle point. For this, maximizing player say A and minimizing player B. So A, B, C, D, P of matrix. First we find row minimum. So here first row A and B, here A and B, A is less than B, so obviously row minimum for this first row is A, and C and D, for C and D, compare C and D, D is the minimum, so second row minimum is D. And column maximum for the first column A and C, so A and C, C is greater, A is less than C, so C is the column maximum, and for the first column, and for the second column, and this B and D, B is greater, so column maximum is B. Now V lower bar is the maximum of the row minimum, so equal to maximum row minimum is A and D. Now A and D, so maximum is D, so V lower bar is D, and V upper bar and minimax value, that is minimum of column maximum, equal to minimum of column maximum C and B. So C and B, C is the B is the C and B minimum is B and C, minimum is B, sorry, and this is the B, not C. Minimum B and C is B, so this is the B, because B is less than C. So V lower bar not equal to V upper bar, because A, B, C, D are not equal, hence the game is non-strictly determined, and so there is no saddle point, hence the correct option is 4, there is no saddle point. Thank you for watching this video.